Last time we saw a rule for logarithms, that logarithms turn multiplication problems into addition problems. And to get it back in our brains, this is what we did. We looked at say, the logarithm of a product of two powers, b to the n and b to the m. Log base b of b to the n times b to the m. Now, b to the n times b to the m, we know from our rules of exponents, is actually b to the n plus m. All right, so we're looking at the log base b of this quantity. Well, what's the power of b that gives this quantity? Well, n plus m is the power of b that gives b to the n plus m. Great. So that was actually the rule that takes a product into an addition. And we just changed the notation of things a little bit. We called this capital N and call that capital M. So n is the power of b that gives the answer capital N, and m is the power of b that gives the answer capital M. Oh, which means I could rewrite this rule as log base b of n times m is the power of b that gives capital N, log base b of n, plus the power of b that gives capital M, log base b of m. There it is. That's how most people present this rule. Great. But we could also do a division version, not a multiplication, but a division version of this rule. Let's start with a variation of the top line. Let's do log base b of b to the n divided by b to the m this time. And our properties of exponents tells me that what's inside there is really b to the n minus m. And what's the power of b that gives this quantity? Well, n minus m is the power of b that gives this quantity. So if I translate that in terms of capital N's and capital M's, this is telling me that log base b of n divided by m is capital N, so log base b of capital N minus log base b of capital M. Great. So actually, logarithms also turn division problems into subtraction problems. Great. People in the 1500s and 1600s start doing all sorts of arithmetic now, multiplications and divisions with the power of logarithms. Okay, that was great and good 400 years ago. But why do people care about logarithms today? What's really going on? We can now do multiplications, divisions, no worries. We've got calculators. So why are they still useful to this day in the 21st century? Well, it's because of another power rule. So let me clean the board and explain the next power rule we will look at for this little video. Okay, consider this rule of exponents. If I take a power of a power, b to the n, and raise it to the mth power, the rules of exponents tells me this is b to the n times m, b to the single power, the product of n and m. All right, so let me phrase that in terms of logarithms. If I take the logarithm of base b of b to the n all to the mth power, this is really log base b of b to the n m. And what power of b gives the answer b to the n times m? Well, it'll be n times m. Right, great, great, great. But we called this capital N at one point. So let me translate what we just wrote in terms of capital N. It's saying log base b of n to the nth power, there's n to the nth power, is, okay, n, well, n is the power of b that gives capital N, log base b of capital N times m. All right, that looks a little strange, but that's little m, that's big N. My handwriting is atrocious. Actually, most people prefer not to use the letter little m here. They prefer to use x. Let me just replace it with x instead. And there we go. Log base b of n to the x is log base b of n times x. And most people actually put the x in front. They say log base b of n to the x is actually x times log base b of n. In the end, this basic power rule here translates to logarithms that the logarithm of something raised to a power is that power times the logarithm of the original number. Okay. This is what people really love about logarithms today. This is the key feature that makes people still want to work with them. Because it says, if you've got a power, if you've got some sort of unknown value, some sort of value of x stuck upstairs, hitting it with a log shakes it down in front. Bingo. Hitting something with a log shakes all the exponents down out front where you can manage them. That is the thing we want to play with, and let me show you why that is so helpful and so advantageous to us today. Here's an example. I have some goop, and the goop is growing continuously at a rate such that it doubles in mass every hour. So at time t equals 0 hours, so let's say I have 1 kilogram of mass of goop to start with. After 1 hour, I have 2 kilograms of mass, doubled. After another hour, at time t equals 2 hours, I have 4 kilograms of mass. After another hour, 8 kilograms. Another hour, I'll have 16 kilograms, and so on and so on. It's continuously growing, doubling every hour in mass. And the question is, when will I have 1,000 kilograms of goop? Assuming I start with 1 kilogram at time t equals 0 hours. All right. So I know from my work with exponents, we actually say what the mass of the goop is at any time t. So we know from previous work on exponents, we know that the mass of the goop at time t is going to be given by 2 to the t. When t is 0, 1 kilogram. Kilograms, I should write. T equals 1, 2 kilograms. T equals 2, 2 to the 2, 4 kilograms, and so on. And the question is, when will this mass equal 1,000? So we need to solve 2 to the t equals 1,000. All right, here's the trouble with this equation. It has the unknown, our t, stuck upstairs. It's actually very, very hard to solve algebraic equations with the unknown stuck upstairs as exponents. Very tricky. However, we know how to get those exponents down to a level where we can manage them. Just hit the equation with a log. Let's hit it with a log. And since I want an actual number, I'm going to use my calculator, and my calculator only has a log base 10 button. I'm going to hit this with log base 10. So let's hit this expression with a log base 10. Log base 10 of 2 to the t would equal log base 10 of 1,000. Okay, hit it with the log. What does it do? Shakes down the exponents. So it says that t times log base 10 of 2 is log base 10 of 1,000. Well, the power of 10 that gives 1,000 is 3. So this tells me that, I'm running out of room. Give myself a little more space here. Okay, making smudges. Can I do it? Can I get myself enough room right now? That tells me t equals 3 divided by log base 10 of 2. I can get it in my calculator. In fact, I did. And on my calculator, when I did it, I got that this is about 9.97 hours. So in about close to 10 hours, I will have 1,000 kilograms of goop. Great. But the point is, we end up with an equation with the unknown stuck upstairs. Very hard to solve equations with unknowns upstairs. The way to handle that is hit the equation with a log and shake down that exponent. Great. And then it's a place we can manage it and use algebra to do it by standard techniques. Great. So let's do a couple more examples, but let me clean the board. Okay, here's a very typical textbook type example, just to practice solving equations with unknowns stuck upstairs. All right, this equation, I have no idea where it would come up in real life. I doubt it ever would, but it's asking 2 to x plus 1. I want that to equal 3 to the x. So I've got an exponent here of x plus 1. The entire quantity x plus 1 is the exponent on the left, and just x is the exponent on the right. So I want a value of x that makes that a true statement. Okay, all right. Well, having exponents stuck upstairs is very awkward, and we can handle that by hitting with a log. That'll shake them down. So let's do that. Here's my answer. Since I'm going to try to get an actual decimal value for x here, I want to use my calculator, and my calculator only has a log base 10 number. Now we can hit it with any log we like, that's fine, but I think I'm going to stick with log base 10, so I'll then use my calculator to actually get a number from that. So let's hit this up with a log base 10. So log base 10 of 2 to the x plus 1 equals log base 10 of 3 to the x, All right, what do logs do? They shake down those exponents. But we're going to be careful here. All of x plus 1 is the exponent right there, so all of that shakes down to the front. And x is just the exponent here, so that will shake down to the front here. So this reads now as x plus 1 times what's left behind, log base 10 of 2, equals x times what's left behind, log base 10 of 3. All right, okay. All right, now it's like an algebra equation. I've got all the x's on the level I want them to be at. I can actually solve this. And I can use my calculator to get these numbers. In fact, I did it. I remember I got x plus 1 times 0.301 is log of 2 is approximately equal to, because that's rounded, x times 0.477, I believe it is. Let me just double check, because I did write it down. 477, yes, that's what I did get. All right, so what have we got? Let me expand this out. X times 0.301 plus 0.301 is approximately equal to x times 0.477. All right, okay, so let me subtract 0.301 x's on both sides, and I can see now that x is going to be about 0.301, it's going to be left over, divided by this difference, which is 0.176. Okay, great. And I did that on a calculator as well, and I got some number. I got about 1.710, I believe. Okay, whoa. So x is about this, but I just did a lot of rounding. I rounded there, I rounded there, I did that, no rounding here, no rounding here, but then I actually rounded my answer here. So a lot of rounding going on. Some people might advise, James, don't work out the decimals until the very, very end. Stick with the actual sort of more abstract expressions right from the get-go. So if I do that, okay, bad board technique, imagine I went this route instead. I can now see that x times log base 10 of 2 plus log base 10 of 2, it's expanding this one out, is meant to equal x times log base 10 of 3. All right, let me subtract x times log base 10 of 2 minus log base 10 of 3 equals log base 10 of 3, which tells me x is, okay, this is a terrible technique, log base 10 of 3 over log base 10 of 2 minus log base 10 of 3. I think I did that correctly. There it is. Grand, grand, and good. So there is the exact answer for what x truly, truly is. All right, and then at the very end, I could do all my decimal approximations right here and do all the rounding in one hit. I probably won't have compounding rounding errors. This might be a little more accurate than this, but great, there's the exact answer. If I really want the decimal value, I could work it out. Okay, here's yet another textbook example. Please solve this ghastly looking equation. Why anyone would want to do this, I do not know. Maybe just to practice our log techniques, because that's why we're doing it. I don't think this will ever come up in real life, but you know, if it's there, if we want to practice our ideas, let's just go for it. I'm definitely seeing unknowns stuck upstairs. And the way to handle unknowns stuck upstairs is to hit everything with a log and shake them down and get them to a level you can handle them. So let's do exactly that. Okay, one thing to be clear. My calculator only has one log button, log base 10. So if I want to get an actual number out of this and use my calculator to help me, I better hit this with a log base 10. I hit with a log, any base log I like, but I think to get a calculator to help me out, I need log base 10. So let's do that. So my answer, here goes, answer. Log base 10 of this product, 5 times 3 to the x, would have to equal log base 10 of this product, 7 times 4 to the x plus 1. All right. I'm going to do something else a little bit sneaky. A lot of people don't bother writing the subscript 10 when you're going to be working with log base 10. They can say, if you're going with a logarithm, just go with 10. Everyone uses 10. In fact, it's called the common logarithm. So some people won't bother writing log base 10. They'll just leave the subscript off. Understood that it's meant to be 10 if it's not there. All right, so I could just erase that smudge, and I would still read that as log base 10, even though there's no 10 showing. All right. But what I'm going to do now, what do I really see here? Well, I've got log, base 10, of a product, 5 times something. So I know that the log of a product is the sum of the logs. Logs turn multiplications into additions. So this is really log base 10 of 5 plus log base 10 of 3 to the x. The sum of the two logs equals. There's another product. A log of a product is the sum of the logs. Log base 10 of 7 plus log base 10 of 4 to the x plus 1. Great. All right, okay. All right, now I've got some unknowns stuck upstairs. And I know logs shake things down. There's an x stuck upstairs, I'll shake it down. There's an x plus 1, all of that's the exponent here. That whole quantity is the exponent, I'll shake that whole quantity down. So this actually reads, okay, getting long and involved, log base 10 of 5 plus shake down the x times log base 10 of 3, that's what's left behind, equals log base 10 of 7 plus shake down all the x plus 1 and leave behind log base 10 of 4. All right, not looking fun. I might want to expand that out. In fact, I will expand that out. Log base 10 of 5, here I go, lots of writing again. Log base 10 of 3, x times, equals log base 10 of 7 plus x times log base 10 of 4 plus 1 log base 10 of 4. All right, now I'm going to be sneaky. I'm going to see if I can just do this in my head, and I'll probably make a mistake. Here goes. I'm going to bring the x stuff to one side, or the non-x stuff to the other, and see what answer I'm going to get. And I bet I will get that x is, okay, hey, can I do this? Log base 10 of 5 minus log base 10 of 7 minus log base 10 of 4, log base 10 of 4, all divided by, and then the x stuff is over here, I would have put this over yonder, so it's going to be log base 10 of 4 minus log base 10 of 3. There is the exact answer for what x actually is. This value here makes this ghastly looking equation true. I'm not surprised the answer looks ghastly as well. In fact, now I can go to my calculator, work out all these things, and do the computation, and I think I did that. Did I get an answer? Yeah, I got x is about negative 5.984 if I'm reading my handwriting correctly. Okay, that's it. Logarithms are fabulous. This is why we like them. If you've got your unknown stuck upstairs, you can hit it with a log and shake it down, and then you can handle it. Even though it doesn't look pretty, you can still handle it. Okay, I did mention that our calculators only have one logarithm button on them, log base 10. This question is asking us to actually compute the value of log base 3 of the number 7. There is no button in my calculator for that. What can I do? All right, let's figure our way through this one. Okay, here's an answer. I know it has some value. It's some power 3 will give the answer 7. How am I going to find it? Well, actually, let's do what I just said. First of all, let's give it a name. Let's call this thing log base 3 of 7. It's going to be something. I'll call it Frederica. F for Frederica. All right. It is going to be this. Frederica is going to be the power of 3 that gives the answer 7. So whatever Frederica is, I know that 3 raised to the power of Frederica is going to give me 7. All right, so I'm really playing with an equation like that. All right, how am I going to figure out what f is in an equation like that? Because my f is stuck upstairs. Well, the answer is hit it with a log. And what log can I hit it with? So I can use my calculator? Log base 10. Let's hit this with a log base 10. So log base 10, I'll write the 10 this time, of 3 to the f is log base 10 of 7. And what does that do for us? Well, hitting with a log shakes down any exponents you've got. F at the top gets shaken down and put out front. So this tells me, in my bad board technique continues, that f times the log base 10 of 3 equals the log base 10 of 7. Divide both sides by log base 10 of 3. Frederica is actually the log of 7 divided by the log of 3 in base 10. And now I can go to my calculator, work that out, and I did it, and I got about 1.771. About 1.771. 3 to the 1.771 is about 7. We did it. We found that value using our calculator, even though our calculator does not have a log base 3 button. Grand.